Welcome you all to the world of physics. Myself Manjusha, PGT Physics JNV Wayanad, dealing with class 12 physics portions. Here we shall focus upon the chapter Semiconductor Electronics, Materials, Devices and Circuits. So, what are the semiconductors? As you all know, the materials which can conduct a little bit, isn't it? That means they are not good conductors like metals, they are not good insulators like good plastic, etc. Rather, they can conduct a little bit. That means they have conductivity in between conductors and insulators. Then, why should we study about the semiconductors? Why they are so important? We are having conductors with lot many free electrons which can conduct large amount of current. Then why should we study about the semiconductors in between? Are they important? Yes. Actually, the development of semiconductor electronics started in early 1930s. Since then, it has brought about lot many changes in the field of technology. As you all know, we have mobile phones with us, laptops, tablets, etc. All such kinds of electronic gadgets are based on the semiconductor materials. And also we know, in olden days we were having very bulky television sets, right, which contain cathode ray tubes. And also such TV sets consume lot many power and also dissipate a lot amount of energy. But nowadays in our homes we are having very small sized, compact, lightweight TV sets which are LED, which are made of LED. That means it is also semiconductor material. So here you can see a circuit board. You might have seen such circuit boards in electronic gadgets, right? So this is a printed circuit board where lot many compact sized components have been soldered, right? You can see the soldering also. So here the components like LED, diode, IC, transistors, all these are based on the semiconductor electronics. That means they are made up of semiconductor materials. So such circuit boards you can see in almost all our electronic gadgets. That means in our daily life we are dealing with lot many electronic components which are based on semiconductor materials only. So here we have a solar lamp. You might have heard about solar devices, solar lamp, which convert solar energy into light energy here, isn't it? And how this light energy is produced from the solar energy? Yes, there we require a solar panel like this. This is solar panel. The solar panel is converting the solar energy into light energy, which you can see in this lamp. Okay, so the solar panel is also made up of a semiconductor material called silicon, right? Nowadays, almost all our homes have having or fabricated with solar panels to have large amount of power from solar energy. Moreover, when we come to the case of light bulbs in our homes, you know, olden days we were having incandescent bulbs, right? They consume lot amount of power and also at the same time dissipated large amount of energy in the form of heat. But nowadays we are using LED lights, right? Which are using very less power and also dissipating very less power. Likewise, when we deal with different kinds of electronic gadgets that we come across in our daily life, almost all the electronic components are based on the semiconductor materials only. So it is necessary that we should study about the basic concepts of semiconductors, right? So children, I hope all of you are ready to explore to the world of semiconductors. So welcome you once again. Let us start with the first part of our discussion of the chapter Semiconductor Electronics, Materials, Devices and Simple Circuits. So what are semiconductors? As we mentioned, the materials which have a conductivity between conductors and insulators, they are named as semiconductors. Resistivity of semiconductors is of the order of 10 raised to minus 5 to 10 raised to 6 ohm meter. So conductivity is 10 raised to 5, 10 raised to minus 6 mho per meter. And the one important peculiarity of this semiconductors is that the temperature coefficient of resistance is negative for these materials. And why the materials are having such property, that we will be discussing in our coming session. And example for semiconductors, In pure elemental form, we can have silicon and germanium as the semiconductors. And these semiconductors exist in the form of compound form also. That means just like organic compounds or inorganic compounds. Inorganic compounds like gallium arsenide, cadmium sulfide, indium phosphate, etc. Several polymers, organic polymers also are there which belong to the category of semiconductors. Now, before going into detail about the basic concepts of semiconductors, let us have a look at the energy bands in solids. Okay, energy bands in solids. That means you know that in every atom, these electrons will be present in certain specific stable orbits, isn't it? Energy levels. But if this atom is coming nearby another atom, that means if a crystal is formed which contain large number of atoms, then this energy levels of these valence electrons will be redistributed because of the interaction of the nearby atoms, and as a result the energy levels will be forming into a certain set of group or set of energy levels called bands, and such splitting up of these energy levels because of the interaction of the neighboring atoms, that is known as the energy band. So let us have a detailed look into the energy band formation in solids. As we told, in every atom the free electron is having a specific energy level. Okay, they can exist only in some definite energy state, and if we are forming a crystal, these energy levels get modified due to the interaction of this neighboring atoms or the electrons of the neighboring atoms. And this interaction is appreciable in the case of valence electrons only. When you come to the case of innermost shells, these electrons will not be disturbed by this interaction of the neighboring atoms. But anyway, the valence electrons, for the valence electrons, these energy levels will be getting redistributed and energy bands will be formed. Now, if you have a look at this one, here this is a plot of energy of this electron in the shell, which are existing in the shell, versus the interatomic spacing. So energy on the y-axis, interatomic spacing on the x-axis, and as we know, the innermost electrons, I told already that innermost electrons will be undisturbed by the interaction of these neighboring atoms. That is, when an atom is coming in bond with the nearby atoms, the valence electrons, the energy levels of valence electrons get redistributed. Okay, so let us have a look at that redistribution of these energy levels. And here all these levels have been occupied by the electrons. Okay, so these levels indicates the subshells. That means, as you might have studied in chemistry, electrons are arranged in subshells in the case of atoms. So S, P, D, F, like that. So here the S subshell can have only 2 electrons maximum, and P can have maximum 6 electrons. Okay, so this is the case with the pure form of semiconductor material, silicon. Okay, so silicon having this particular electron configuration, that means 1s2, 2s2, 2p6 and 3s2, 3p2, because as we know silicon is having atomic number 14. Okay, so this electron distribution will come like that, and as we know the outermost shell is having 4 electrons, 3s2, 3p2, you can see that 3s2, 3p2, and when the interatomic spacing is very large, you can see all these electrons are existing in certain specified energy levels, isn't it? But as this particular spacing becomes smaller, let us see what will happen to this energy levels. So this 1s2, 2s2, 2p6, those electrons are considered to be the innermost, so ion core state. Okay, they are in stable state, and we are considering the 4 points here, A, B, C, D, like that, to understand that redistribution of this energy levels of the outermost electrons. Okay, so you can see that at the point D, okay, that means when R is equal to D, you can see that there is no particular change in the energy levels of the outermost shells. Okay, and as the distance is reduced, R value is getting reduced, R when it approaches C, you can see that the energy levels of 3s2 and 3p2 electrons get almost, they are trying to get mixed up. That separation is getting reduced. You can see the gap is getting reduced. And at the point B, that means R is equal to B, you can see that 3s2 and 3p2 electrons, that means the electrons present in the S subshell and the P subshell, they have been mixed up. The energy levels of these electrons have been mixed up at the point R is equal to B, right? So at this region, we are not able to separate out which are the S electrons or which are the P electrons, because all the 4 valence electrons exist in the mixed state. Okay, and that means in that region there is no energy gap at all. There is no difference between the energy levels. All the energy levels have been mixed up. And again, if the interatomic spacing is reduced at the point R is equal to A, you can see again the energy levels get separated. Okay, and a small gap has been formed there, and this particular lower energy level, I mean that group of levels, okay, which contain all the 4 valence electrons, okay, all the 4 valence electrons, that is corresponding to the valence band. And we can have another 4 more levels in that same shell, okay, and but these levels are completely empty in the case of silicon atom. Okay, so in that particular band, that means band, I already mentioned, it is the collection of energy levels. So that particular band is called conduction band. So valence band contains the electrons, that means valence electrons of the atom, and the conduction band contains actually the conducting electrons. But in the case of silicon, there are no electrons present in the conduction band. Okay, so and also this bands, there is a energy gap between that particular 2 bands, and that energy band is named as forbidden energy gap. Okay, forbidden energy gap is the energy gap between the valence band and conduction band. Okay, so this particular energy level redistribution happens when the atom come in the close proximity of another atoms. Okay, they will be forming bond with the nearby atoms when that solid or the crystal is formed. So during that crystal formation, such an arrangement, that means such a redistribution of energy levels happens, and they exist in the form of bands, energy bands, valence band containing valence electrons and conduction band containing the conduction electrons. And here in this example, since we refer to silicon atom, conduction band contain no electrons at all at this particular situation. And so how we are able to make the silicon or semiconductor conduct? Okay, that we will be discussing in our coming session. Okay, so the same what and all we have discussed is mentioned here at R is equal to OD. That means that far when the distance is far away, distance between the atoms are somewhat far away, then each electron has their own specific energy level. They are distinct or separate. But as the distance comes closer, that means the atoms come closer, the energy levels get splitted up. Okay, they start splitting up, and at a particular region the interaction will be maximum and the energy levels will be splitting, and thereafter these energy levels are getting mixed up. That means, as we told, the S electrons and P electrons get mixed up, their energy levels are mixed up. We are not able to separate out these S subshell electrons and P subshell electrons. And finally, the energy levels, very close energy levels will be forming as a band, and that such a collection is known as energy band. And but at a particular point, as we mentioned, this energy gap completely disappears, and after that the energy band, that means valence band and conduction band, will be forming, and the forbidden energy gap is the energy gap between the valence band and conduction band. The lower completely filled band, that means the band which contain valence electrons, that is known as valence band, and the unfilled band is known as conduction band. This is the case particularly with the silicon only. Okay, so that's why conduction band is empty here. Now the same case, valence band and conduction band, the definition. Valence band and conduction band, there are two different energy levels separated by a certain amount of energy. And the main difference between valence band and conduction band is that valence band specifies the energy level of electrons present in the valence shell of an atomic structure. Okay? And the conduction band, it specifies the electrons which are responsible for conduction. And forbidden energy gap, it is also referred to as band gap. Okay? And this is the energy difference between the top energy level of valence band and the bottom energy level of the conduction band. And this normally this energy difference is mentioned in the unit of electron volt, EV. Okay. So 1 EV, already we know the definition. It is the energy acquired by one electron when it is accelerated through a potential difference of 1 volt, and it is equivalent to 1.6 to 10 power minus 19 joule. Okay. And this energy gap or the band gap in the case of silicon, it is 1.11, and for germanium it is 0.67 electron volt. Now let us have a comparison of this energy bands. That means such energy bands will be formed in the case of all kinds of materials, whether it is semiconductor, insulator or metals. So let us have a look at the energy bands of these three categories, that means metals, semiconductors and insulators. Already we know that the insulators are having no free electrons, that means no conduction possible there. But metals are having lot many conducting electrons, and semiconductors have conductivity in between that of conductors and insulators, or metals and insulators. So let us see how we can classify these three in according to the energy band. So as you can see, for insulators the band gap between conduction band and valence band is very large. It is of the order of 3 electron, that means more than 3 electron volt. For insulators the energy gap or band gap is greater than 3 electron volt. Okay, so that is why there is no conduction electrons in the conduction band. Okay, so but at the same time we can see that semiconductors at band gap is somewhat reduced. See, so from the valence band, if the electrons are able to reach the conduction band by somehow overlapping that gap, then only the conduction is possible. So since the semiconductors, since they have less band gap, if we are supplying external energy in the form of electric field or heat, okay, then these electrons can reach the conduction band, thereby making the conduction possible. Okay, but for insulators there is no such possibility because the band gap is very large. Clear? In the case of conductors, you can see there is no gap at all. For some conductors, actually the valence band and conduction band will be overlapping. So there will be large number of free electrons or conduction electrons present in the conduction band, which improve or which provide highly conducting material for us. Okay, but in the case of certain conductors, there will be a minute gap between valence band and conduction band, which gap the electrons can easily jump and reach the conduction band. Hence conduction will be possible easily for such conductors also or metals also. So this is the difference in the energy band diagram for metals, semiconductors and insulators. I hope it is clear to all of you. Nextly, we have to discuss about the charge carriers in semiconductors. We know in metals the charge carriers are electrons, okay, negatively charged electrons. But in semiconductors, in addition to electrons, we are having one more term, that means holes. So here holes as well as electrons, they are the type of charge carriers, which is the reason for the flow of current in semiconductors. So what are these holes, or how these holes are produced? So we know that the electrons which are present in the valence band, okay, they can reach the conduction band if they acquire energy. Okay, so when such electrons acquire or absorb energy and reach the conduction band, this electron will leave a vacancy in that valence band. Okay, so that vacancy, which is equivalent to a positively charged particle, that is named as holes. Okay, so the concept of hole we will be discussing in detail. Now, types of semiconductors. Semiconductors are of two types mainly, that is intrinsic and extrinsic semiconductors. Intrinsic semiconductors means they are pure semiconductors, single type of element. As we mentioned, silicon, germanium, they are pure form or intrinsic, okay, inbuilt. Okay, there is no impurity, pure form, intrinsic semiconductor. And another one is extrinsic semiconductor, where we will add some impurities to this pure form of semiconductor to improve the conductivity. So extrinsic semiconductor means actually it is an impure semiconductor. We will be adding impurity to the pure form of semiconductor so that we can have better conductivity with such material. Nextly, what are these intrinsic semiconductors? We have to study in detail. As we mentioned, the pure form of semiconductor is known as intrinsic semiconductor, and silicon and germanium examples. So let us have a look at the electronic configuration of silicon and germanium. Silicon already we mentioned 1s to 2s to 2p6, 3s to 3p2, the outer shell having 4 electrons with the atomic number 14 for the silicon. And germanium at the same time atomic number is 32, and hence the electronic configuration is 1s to 2s to 2p6, 3s to 3p6, 4s to 3d10, 4p2. So here also you can see the outermost shell of germanium contain 4 electrons. That means silicon and germanium are tetravalent. Okay. So they are tetravalent with valency 4 electrons in their outermost shell. So because of this 4 electrons or the tetravalent nature, this silicon and germanium will be forming covalent bond. That means they will share the electron, the valence electron with the neighboring atom, thereby forming covalent bond. So the crystal structure of silicon and germanium will be as shown. They will be sharing one electron with the nearby silicon atom, forming a structure like this, and this is a stable silicon crystal. Okay, and now we can see the concept of hole in detail. So if we are giving some energy, that means external energy in the form of heat or electric field, this electron in the valence band can reach the conduction band. Okay, and hence they can take part in the conduction. So this movement of electron from the valence band to the conduction band creates a vacancy in the particular valence band, and this vacancy will be having a positive charge because that is always ready to accept electron. Okay, there is a vacancy of electron means that is always ready to accept electron, hence it is having a positive charge, and we will name it as a hole. So from this figure you can have a look at the formation of hole. That means from the bond one particular electron has been made free, thermally generated free electron. That means because of the heat energy that electron become free, and there a hole or a particular vacancy has been created, electron vacancy, which is named as hole. So these electrons and holes both are taking part an important role in the conduction for the case of semiconductors. So this hole will be formed in the valence band, and similarly I told you that this hole is always ready to accept an electron. So from any other neighboring bond, an electron which is free, that means an electron which acquire energy, can hold that particular position or that particular vacancy. Okay, that means electron from the neighboring bond can become free and it can accommodate that vacancy of the previous electron. Okay, as likewise we can see that there is a movement of holes also in case of semiconductors. That means as the electron is moving forward, you can say that holes are moving backward. Okay, so the electrons as well as both are having an important role in the case of conduction for semiconductor material, and holes also move randomly in crystal lattice. And this particular unique property, that means only the semiconductors are having holes also as the charge carriers, and their movement also contribute to the conduction of electricity in semiconductor. And as we mentioned, when one electron is jumping from valence band to conduction band, or one electron is becoming free, that electron is leaving behind a hole. That means When a bond is broken, the number of electrons becoming free, the equal number of holes will be created. That means the number of electrons and holes in such a particular material will be equal. And the hole is having the charge similar to that of electron but of opposite polarity. You can see as the electron got transferred from valence band to conduction band, it has created a vacancy or hole in the valence band. Now we are having a look at the intrinsic of pure semiconductor germanium, and from germanium how this particular electron is able to break the bond, applying heat energy. The electron is breaking the bond, covalent bond, and become free. Likewise, several electrons from different sides of the crystal lattice can become free by absorbing that heat energy. And you can see that the previous hole created by the vacancy of another electron, that hole was occupied by the electron from the neighboring bond. Likewise, electrons as well as holes both are taking part in conduction. Okay, in the case of semiconductors. So from the valence band, electrons are getting jumped from the to the conduction band, and as a result holes created. Okay, that is shown in the figure. Now, carrier concentration in intrinsic semiconductor or pure semiconductor. As we mentioned, current flow is due to the flow of both holes as well as electrons. Therefore, not only the electron current, hole current also contribute to the total current in the semiconductor. So the total current will be electron current plus hole current. And here, as we mentioned, number of electrons and holes will be equal. Ne is equal to Nh in the case of semiconductors or intrinsic semiconductors. Then this quantity Ne or Nh, that is known as intrinsic carrier concentration. And this is the, as we mentioned, the stable form of silicon crystal, that is at T is equal to 0 Kelvin or absolute 0, it will be in a stable form. And as a result, all the bonds, they are very tightly bound, all the electrons. Okay, so there are no free electrons present in the crystal lattice. But if the temperature is more than this, that means if you are giving heat energy to the crystal lattice, then definitely this some of the electrons from different sides of the crystal can become free, and hence it can improve the conductivity of the semiconductor material. So at 0 Kelvin, the intrinsic semiconductor acts as an insulator only. So the energy band diagram, as we mentioned, at T equal to 0 Kelvin, it behaves as an insulator, and T greater than 0 Kelvin, there will be thermally generated electrons present in the conduction band. At the same time, holes in the valence band. Now, doping a semiconductor. We know that the intrinsic semiconductor, the conductivity of intrinsic semiconductor is limited, because by giving heat energy or by giving some external energy only we can have or we can improve the conductivity of such intrinsic semiconductor material. Okay, but there is a limit for that. So there is another technology or technique called doping. Doping means we will be adding some impurities or another atoms to such intrinsic or pure semiconductor, so that the conductivity of the material will be improved. Okay, let us see how it is happening. Before that, what is doping? So the process by which an impurity is added to a semiconductor is known as doping. And the purpose of adding impurity is to increase the number of electrons or holes, that is to make it more conductive. And the impurity atoms are called dopants. Okay. And depending upon the type of impurity added, the extrinsic semiconductor can be classified as N-type or P-type semiconductor. So extrinsic or impure semiconductor can be classified into two groups, N-type and P-type semiconductors. Now, this extrinsic semiconductor, that is N-type semiconductors, here the germanium, the pure form of germanium crystal, then into that crystal we will be adding an impurity. Okay, and here the impurity we are adding is arsenic. Okay, arsenic atom you can see there, which is a pentavalent atom. Okay, that means valency 5, group 5 elements. So this particular arsenic having 5 electrons in the valence shell, you can see that the 4 electrons of the arsenic will make covalent bond with the 4 neighboring germanium atom, and 1 electron of the arsenic will be left free, isn't it? So that electron is free, which will be improving the conductivity of this particular germanium material. Okay, so here we have seen only one arsenic atom. Likewise, doping means a small concentration of the impurity atom will be added to the pure form of semiconductor. So different sides of the germanium crystal will be containing or will be replaced, germanium atom will be replaced by arsenic atom. So as a result, each arsenic atom contribute 1 free electron to the crystal lattice. Likewise, the number of free electrons in the crystal lattice increases, thereby improving the conductivity of semiconductor material. And in addition to this free electron created by the dopant, there can be thermally generated electrons also. Okay, and the same concept of, that means hole also will be present in the crystal. Okay, so likewise in the extrinsic semiconductor or n-type semiconductor, there will be large number of electrons. Okay, that means number of electrons will be more than number of holes, because here there are electrons present due to the impurity atoms as well as thermally generated atoms. Okay, so that's why such semiconductors are named as n-type, more number of electrons or negatively charged carriers, therefore they are named as n-type semiconductor. And the band diagram of this n-type semiconductors, we can see that the valence band and conduction band refers to that of pure germanium. Okay, and there the energy gap is about 0.7 electron volt, and in between you can see a dotted line which is showing the donor atom level, that means energy level of the impurity atom which we added, that means arsenic here. And you can see that the bottommost energy level of conduction band and the donor level, in between those two levels there is a minute energy difference only of the order of 0.045 electron volt. So the free electrons which are present in that donor level can easily reach the conduction band of the germanium crystal, isn't it? Thereby improving the conductivity of the semiconductor material. In addition to that, free electrons given by or donated by the impurity, there will be thermally generated electrons also, but you have to keep in mind here number of electrons will be more. Okay, because there will be electrons donated by the impurity atom addition to the thermally generated electrons. Okay, so this is the case with n-type semiconductor. So this is silicon, the case of n-type semiconductor with the silicon, that means silicon crystal has been doped with the phosphorus. Okay, which is also a pentavalent, so 1 electron becoming free. That also clear from the figure. Now as we mentioned, the energy state corresponding to the fifth, that means the donor level will be nearby the conduction band of the pure semiconductor material. So easily the electrons from the donor level can reach the conduction band, thereby improving the conductivity. Okay, so if N and P represent the electron and hole concentrations in the n-type semiconductor, then the product N into P, that means number of electrons into number of holes, that will be equal to Ni square, where Ni stands for the intrinsic carrier concentration that we mentioned in the case of intrinsic semiconductors. So actually the product Ne into Nh will be same as Ni square, that means when you multiply the number of holes and electrons in the case of intrinsic semiconductors, that will be Ni square only. Okay, because their number same. But here number of electrons, when we add the impurity, that means pentavalent impurity, number of electrons become more compared to number of holes. Okay, so this particular product, anyway the product of number of electrons and number of holes will remain same, because when the concentration of electron is increased above the intrinsic value by the addition of donor impurities, the concentration of holes falls below, because of the recombination. Some of the electron will recombine with the holes already present. Okay, so that's why even though number of electrons are getting increased, number of holes already present may decrease. Thereby the product N into P or Ne into NH will be equal to Ni square. Now the case of next category of extrinsic semiconductor, p-type semiconductor. Here we are considering a silicon crystal doped with a trivalent impurity. That means the group 3 elements belong to group 3. Okay, trivalent means they have only 3 electrons in the valence shell. So these 3 electrons will be making bond with the neighboring 3 atoms. Okay, but there is one vacancy of electron to form a bond. Clear? So that vacancy means it is a hole in the crystal lattice. So this p-type semiconductor we are forming by doping the pure semiconductor with the trivalent impurity, and it will be creating a hole in the crystal lattice. As you can see, the energy level of the acceptor atom. Here the impurity is known as acceptor because it is producing or it is giving a hole, isn't it? Hole in the crystal lattice, giving rise to hole in the crystal lattice. Hole means it's always ready to accept electron. So that's why it is known as acceptor or acceptor atom. So the energy level of that acceptor atom is just above the valence band of the pure semiconductor, and this energy gap between the valence band and the acceptor level is very, very small, of the order of 0.05 electron volt. So what can happen? From the valence band, the electrons can go to the or jump to the energy level of acceptor atom. Okay, thereby producing large number of holes in the valence band. Okay, so in p-type semiconductor, as we expect, the more number of charge carriers will be holes. Okay, because the acceptor impurity is contributing a hole to the crystal. So there will be electrons present which are thermally generated and also holes. Okay, but additional holes are contributed by the impurity added. So that is what is shown here, and this is the case of the same silicon crystal doped with indium, where a hole has been created or vacancy of electron has been shown. Now energy band diagram of p-type semiconductor. Okay, so as we mentioned, the acceptor level will be just above the valence band, and hence the electrons from the valence band can easily jump to the acceptor energy level and can improve the number of holes present in the valence band, thereby improving the conductivity of semiconductors. Now charge carriers in the extrinsic semiconductors, as we mentioned in the case of n-type, the same is applicable for p-type also. That means the product of number of electrons and number of holes will be same, I mean equal to the Ni square. Ne into NH is equal to Ni square. It is applicable to both the type of extrinsic semiconductor. But anyway, in any of these extrinsic semiconductor, one type of charge carriers will be dominant, isn't it? That means in n-type semiconductors we mentioned there will be more number of electrons present, but in p-type there will be more number of holes present. So the dominating charge carriers, they are named as majority charge carriers, and the other types are mentioned as minority charge carriers. But one main point, even though there are more number of electrons in the n-type semiconductors, they are electrically neutral. Okay. Similarly, even though there are more number of holes, positively charged holes in the p-type semiconductor, they are electrically neutral. How they become electrically neutral? Because this extra electrons which are present in the crystal lattice is a part of the particular atom or the impurity which we added, isn't it? So as a whole, when we take the material, the total charge will be 0. Clear? Similarly, the case of p-type semiconductor also, the hole created is actually a vacancy of electron, isn't it? The atom which we added a trivalent impurity was actually neutral one only, right? So there we didn't taken out any electron from the material, or we didn't introduce any new electron, isn't it? So as a whole, the total charge of semiconductor will be 0, or the semiconductors are electrically neutral. Whether it is extrinsic or intrinsic semiconductors, they are electrically neutral. A very important point to keep in mind. Then in p-type semiconductor, as we mentioned, number of holes larger compared to number of electrons. In n-type semiconductors, number of electrons very very large compared to number of holes, but they are electrically neutral. Now the conclusion of this particular classification of intrinsic and extrinsic semiconductor material. That means intrinsic semiconductor, they are pure form of semiconductor, belong to group 4. Whereas extrinsic means we are adding impurity either from group 3 or group 5 elements. But intrinsic semiconductor is having very little conductivity only, but here in the case of extrinsic semiconductor, conductivity can get improved, okay, by doping. So here intrinsic semiconductor, temperature, giving temperature only can improve the conductivity, whereas for extrinsic semiconductor, by adding the impurity we can improve the conductivity. And here the number of holes is always equal to number of electrons in the case of intrinsic semiconductor or pure semiconductor. But as we seen in the impure semiconductor, one type of charge carriers will be dominant compared to the other based on the impurity which we are adding. Okay. So this is the end of part 1. Okay.